We're not happy with
To start off with our code review, we'll first start with our distance finder function. So we have a get range function, which is defined the same way that it was defined in the lecture slides. And we have a callback function that gets called. It's subscribed to the laser scan topic. And this publishes to the error topic, which the control reads. So we start off by, we know that the angle, the theta, pointing directly to the right is negative 90 degrees, and we found that offset of 60 degrees worked the best. So we ended up going with an average ray approach where we took multiple rays and found the distance using multiple rays instead of just one. This helped reduce the NaN values a lot, and in case we do get NaN values, we just decrement the theta value by 1 until we got a non-NaN value. We also ended up using the error projection as outlined in class, and we'd also measure the distance to the front using the LiDAR array, similar, but we use a theta of 0 this time because we want directly to the front, and this is published as the PID error and velocity message error. So in our control.py file, we read the errors, and we have two parts here. We have the steering PID, which directly controls the angle of the steering using mainly KP and KD. We don't really use a KI here. And then we also have our velocity PID, which scales down the max velocity based on the error. So the larger the error, the more we're going to have to turn. So we want to slow down the velocity, and also compared to how close we are to the front wall, which is what we published on the PID vel. So the closer we are, the slower we want to go because we're going to end up turning anyway. And then using the Ackerman drive, we end up directly controlling the steering angle and the velocity. And here's just how we get our inputs to begin with.